Thank you very much for coming. As many of you know, this is now the third time in a row that we've managed to invite somebody from the Physics Nobel Committee to tell about this year's fresh prize. And you may also remember Mats from last year when he talked about the LIGO prize. This year is even a better match because this is actually Mats's field, and he was the one who did the popular science presentation at the announcements of the Nobel Prize, if you watched it. So we're very much looking forward to your talk, and there will be time for questions afterwards. So please, Mats.
Thank you. And thank you in particular for the invitation to allow me to come here to Oslo and give this presentation. And I have more time here than I had at the press conference where it's very regulated. So let's see now. How do I get... yeah. Okay, yeah, that's. So let me just remind you about Alfred Nobel's will, because sometimes people don't quite realize what we can award a prize for. And what is written in the Nobel will concerning physics is that it should be the person who has made the most important discovery or invention. So this is important that one has to really focus on these two words, either discovery or invention. In a few examples also both. In chemistry it's actually different. It's discovery or improvement. So that makes it different for the chemist when they have deliberation about the prize. I also like to mention that a prize can be divided. It can be divided in two parts with two different citations. According to the rules, there is no requirement that there should be a connection between the two parts. The only criterion is that each part should be standing on itself, so to say. It should have sufficient height to motivate the prize. It is not possible to have three different citations. And there is a maximum number of 3 people that can be awarded a prize in physics a given year, which means that if you have a divided prize, it can be 1 plus 2. And this is really a diabolic construction because it makes it quite tough if you want to have a divided prize. It would have been easier if you had 2 plus 2, but that's not allowed according to the rules. So just to give you an example of a divided prize where there were very little connection between the two parts. This was the 1978 prize where one part went to Penzias and Wilson for their discovery of cosmic microwave background radiation. And the other part went to Kapitsa for his basic invention and discoveries in the area of low-temperature physics. And I had a chance to discuss this a couple of years ago with the only, at that time, surviving member of the Nobel Committee who was involved in this prize. And I asked him, so I don't see any connection at all between these two parts. And he said, well, you know, Penzias and Wilson, they were using liquid helium to cool their detector. And of course, Kapitsa invented liquid helium, so that was the connection. This year, we have a stronger connection, definitely, but it is a divided prize. So here, in this case, we had like a headline first, an umbrella headline, for groundbreaking inventions in the field of laser physics. And one part went to Arthur Ashkin for the optical tweezers and their application to biological systems. And the other part went to Gerard Moreau and Donna Strickland for their method of generating high-intensity, ultra-short optical pulses. And one can note two things here with this prize. Arthur Ashkin is, with a rather broad margin, the oldest Nobel laureate ever. He is actually 96 years old. And of course, you also note that this is the third woman who has been awarded the Nobel Prize in Physics. Last time was 55 years ago. So let's first look at the optical tweezers and what Ashkin was doing. He first, he was looking into the possibility of affecting small micro-sized spheres, transparent spheres, with a laser beam. And he noted that he could push these spheres using the radiation pressure from the laser. He also noted that the spheres like to stay in the middle of the laser beam where the intensity is highest because of so-called gradient forces. And finally, he noted that by focusing the laser beam, one could trap a transparent sphere in the focus. And the reason for these different forces is that here you have a transparent sphere in the middle of a laser beam. And we know that the photon carries momentum. And when the photon is redirected in this direction, there will be a net force acting on the sphere in this direction. And the same for the beam coming in from the other side. There will be a net force like this, and there will be a net force pushing the sphere in the upward direction. Also, if the sphere is a little bit displaced with respect to the middle of the laser beam where the intensity is highest, the force, the F1 force here, will be weaker than the F2 force, which means that the sphere will be pushed into the center of the laser beam. And finally, if you focus the laser beam and you are a little bit off center, here's the center of the focus. In the case the sphere is a little bit below this, there will be a net force pushing the sphere up towards the focus center, and the same if the sphere is a little bit above the focus, it will be pushed down. And this is what makes it possible to trap this little sphere, which can be about 1 micron or so. And here's shall we see if this works, a demonstration using a hairdryer and a ping pong ball. Nope. Can't get this one to work. Okay. So the idea here was to show that you can keep the ping pong ball in the vertical position, but you can also tilt this hairdryer and still keep the ping pong ball trapped. And this is a force which is rather similar than to the gradient force. You have streaming air around it. I don't know understand quite why it didn't work, but it's always like this with animations or videos. So, important references. Well, the first paper was already in 1970, acceleration and trapping of particles by radiation pressure. And this is basically what I just showed you. And then observation of a single gradient force optical trap for dielectric particles. So you see it was quite a long gap here in time. And then came the 2 breakthrough papers, which really motivated this year's prize. And this was the demonstration by Arthur Ashkin that one could trap and manipulate viruses, bacteria, and even living cells. But what he discovered was that initially he was using a green laser light beam for trapping these dielectric particles. But it turned out that biological systems, they don't survive in the green light, but they survive in infrared light. So he just went and used, as emphasized in the title here, infrared laser beams instead of a green laser beam. And this gave rise to nowadays a wide variety of experiments using optical tweezers applied to biological systems. And here is one example that we used in the press conference to demonstrate how it can be used. And this is a motor molecule that walks. A motor molecule, if you remember, there was a Nobel Prize concerning motor molecules a couple of years ago. And these are molecules that are performing work in a cell. So this kinesin molecule, which is a protein, is then, shall we say, converting chemical energy to mechanical energy. And in this particular demonstration by Steve Bloch's group at Stanford, a sphere is attached to the protein molecule, and this is standing on a cell skeleton. So what will happen here is that this kinesin molecule will start to walk on the surface, and at the same time dragging this sphere behind, walking in this direction and then having a force pulling in the other direction. And eventually the kinesin molecule can no longer keep, the restoring force is just too big, and everything flips back to the center of the trap. And by doing this experiment, Steve Block could measure the step size that the kinesin molecule did. Here you see as a function of time. So this is typically distance in nanometer. So here's each step the molecule is doing. And he could also get an estimate of the restoring force, which was in the piconewton range. So this is one example of how one could use this optical trap to really study on a single molecule level the interaction between the kinesin molecule and the cell surface. And here is another more of a, shall we say, artist view of how one can do measurements with the biological system. This is a DNA where they have attached fluorescent atoms so that one could illuminate the DNA molecule and then attach it to two spheres trapped in optical tweezers, and then measure by moving the two spheres with respect to each other. You could get an understanding of how the DNA molecule is performing. And here's another example from a group at Georgetown University, where where you have one sphere which is really locked. The other one is in an optical trap, and there is a DNA molecule here, and then attached to a target protein. And by moving this optical trap with respect to this one can measure the force needed to stretch the protein. Protein usually is in a curved position or folded position, but one can stretch it out and then measure the force it takes to stretch the protein molecule. Here is another example of a bacteria trapped in a optical tweezers. And of course, this looked like a rather simple setup, but if you want to build a system for studying this, one way to do it is to start with a microscope, and then so you have the optical imaging systems and so on, and there is even, as you can see here, there are even now commercial systems for optical tweezers, and of course with this possibilities you can make the system much more applicable than if you have to start from scratch and building something. So I think that this was a very important step to study biological systems. And last week I had, just by accident, had lunch with a colleague who is much more into biological physics than I am. And he told me that, and he's not a member of the academy, but he told me that I've listened to hundreds of talks where people are using optical tweezers, but I never had any idea about who invented it from the beginning. And of course, it was invented in physics. And it was invented in physics only 10 years. The start of this invention was only about 10 years after the first laser was built in 1960. Okay, now I will move over to the other part of the prize. And let's go back now in time to the mid-1980s and see where laser technology was standing at the time. So there had been a development from the 1960s with something called mode locking. development of, or invention of dye lasers, and then developments of the mood locking technique. And it had reached, I would say, a maturity with the typical parameters for the state-of-the-art systems: 5 femtosecond pulse duration, 1 gigawatt average energy, average power, and focused intensity of about 10 to the 15 per square centimeter. And this technology was well suited for studies of movements of atoms in molecules. You could study short-lived transition states in chemical reactions in real time for the first time. And this led to the Nobel Prize in Chemistry to Ahmed Zewail in 1999. But he was given the prize by himself. So the persons that had developing this enabling technology, they were not recognized by the chemistry committee at that time. So, these laser systems were, of course, research systems. I mean, it took a lot of work to run them. Everybody, if anyone has worked with the dye laser, I have worked with it a long time ago. I mean, it's really a lot of labor, and it takes a lot of adjustment and so on to get an experiment running. And usually, if you do this ultra short pulse with the older type of systems, I mean, it probably took the whole morning just to get the laser reasonably stable to do experiments. As I mentioned, I mean, the upper limit for pulsed, for focused intensity was 10 to the 15. And there was no really roadmap to higher intensities or shorter pulses by this time, mid-1980s. There were a few efforts using really brute force, very expensive laser systems that could only be built in national laboratories, like in Lawrence Livermore, for example, and where they could just scale up everything, make very big laser beams and so on. But the rep rate of these systems was very low. I mean, you could do maybe a few shots per day, and then the amplifier had to cool down, and several hours later you could make another shot. And this was a system developed just for fusion research. It was not these systems could not be implemented in university environments, and could not be used for any experiment that require any sort of reasonable repetition rate. So this is the scenario now where we moved to Donna Strickland and Gerard Moreau. And what they did in 1985 was a short paper in optics communication, where they demonstrated how one could amplify chirped optical pulses. And this is the original drawing from the paper, where you start with a mood-locked laser, neodymium YAG laser. Then the optical pulse is then sent into a 1.4 kilometer single mode fiber, so that the pulse is stretched in time. Then it goes into a regenerative amplifier. The pulse is amplified, and finally, in the final step, it is compressed. So that you start with a low intensity pulse, you send it in, you stretch it in time, amplify it, and then you compress it. And here is a more, shall we say, modern version. The first step that happened after they had demonstrated this technique was that the optical fiber was replaced by a pair of gratings. So that one uses, in this case, 2 gratings to have a stretching of the pulse. So you can see here's the short pulse coming in. It is stretched, goes through the amplifier, is amplified, and finally, in a grating pair, it's compressed again so that you have a strong amplified pulse. This may seem like a rather simple arrangement. They did not invent the chirped pulse technique in the sense that it had been used in microwave, in radar technology. And if you read the paper, this short paper in optics communication, which is the breakthrough paper, they refer to an article in Scientific American where they got the inspiration how to do this in the optical region. Of course, one should realize that going from microwaves to optical region is a big step. And this is very clear if you look at what happened in the 1950s, when the maser was first invented by Charlie Townes and the two Russians, Basov and Prokharov. And then when Townes and Shavlov took this technology up to the laser to do it in the optical region, it was really a big step. And of course, they were, these three, the two Russians and Charlie Townes, they were awarded the 1964 Nobel Prize for the laser maser principle. And Shavlov had to wait until 1981 to get a prize in laser spectroscopy. So, what is a chirped pulse? I should mention this because this is the maybe not familiar to everybody. So here you see this is the electric field component of an optical pulse, and this is a time duration stretching from, well, about 40 femtosecond. And what you see here is that the frequency of this pulse is increasing as a function of time. So here is the frequency is lower, and here the frequency is higher. And I like to think in an analogy with an acoustic pulse. How would acoustic pulse that is chirped sound like? Well, then, if you have ever listened to, for example, the Magic Flute, first act, Papageno's first aria, when he's singing how he's a bird catcher and so on, then he has a flute. And when he's blowing in these flutes, the ramp, you see, it's ramped up in frequency. It's much more interesting than if he would be blowing a constant frequency. So that this is the way I think about chirp pulses. And in music, they are much more interesting. But of course, also extremely useful in optical laser physics. So the work that I showed you here, this was Donna Strickland's PhD work, basically. That was the core of her PhD work. And she was the one who had to put together all these components and demonstrate that it worked. And it was also her first scientific publication. So this is an interesting twist, I mean, that she came in as a PhD student, her first work, and of course at that time they couldn't realize what an impact this would have. And I think it was mainly motivated by fusion research. I mean, how can you continue doing fusion research without having to build this enormous, such an enormous laser system working at a low rep rate? And we also did some background check to see who was the person who did the first conference presentation of this work. And it turns out that, so the publication was late 1985, and then in 1986 there were two conferences, one in San Francisco on lasers and electro-optics. And Donna Strickland was the first author on that paper, or that conference contribution. And the same for the Fifth Optical Society American Topical Meeting in Colorado. Donna Strickland was once again the first author on that. So presumably she was the one who presented this at these two conferences. So let's look at now the development of the focused intensity. I mentioned that in the mid-1980s, the focused intensity was 10 to the 15, and there was no real roadmap how to increase this intensity. But with the invention of the CPA technique, chirped pulse amplification, there was a steady increase all the time in the focused intensity, and doubling about once every 4 or 5 years. And so here is this focused intensity. Here is the energy for an electron in an atom that is exposed to this laser intensity. You will have a quiver motion of the electrons, and the energy of this quiver in motion is displayed on this axis here. So it's really, so here you can see when you reach the relativistic electron limit, and here is the relativistic ion limit, and one can go further up. But and this is another way of demonstrating it. Once again, the focused intensity here and the year here. And the first ever laser was built by Theodore Maiman, an American physicist, and this was the intensity. Then there was a development of Q switching, mode locking, up to this point here, late 1960. Then there was this plateau where the pulses got shorter, but the intensity didn't just stay the same. And then finally the invention of CPA, and then this steady growth in intensity. And here we have new facilities that are being developed now in Eastern Europe called Extreme Light Infrastructure. And this is funded by the European Union. And I will show you something about that later. But let's look at the how one can apply these pulses in different regimes. Because there is a relation between the intensity and the rep rate. You can, for some applications, maybe you just need 1 pulse per second. So a rep rate of 1 hertz. Ultra short pulses, 10 to 100 femtoseconds. There are other applications where you need a higher rep rate, maybe 1 kilohertz, which means that you drop a little bit in intensity, but you get many more pulses per second. And finally, there is applications where you need to drop even further in intensity, but you want to have a high rep rate, say 150 kilohertz or so. If we look at the middle range here, the 1 kilohertz rep rate, there you have intensity which is high enough to really cause an electron shell in an atom to be really distorted. I mean, if you have a weak intensity, a photon coming in on an atom can lead to excitation. If you increase the intensity, it can lead to multiphoton absorption and multiphoton ionization. If you increase the intensity even further, you get to a point where the potential is in which the electron is trapped is so distorted, so you get something called tunnel ionization. So the electron is here tunneling out and not, so it's such a big distortion of the electron shell or the potential here so that it's causing tunnel ionization. And what was realized then when people started to get access to CPA-based laser systems, because you saw this explosion in intensity, how it increased, and more and more university groups could get access to high-intensity laser pulses. So there was a new field of atomic physics, which is called strong field physics, developed. And what was realized then was that if you have this situation with tunnel ionization, the electron is liberated, but it doesn't really escape very much far from the atom before the field is switched, so that the electron is once more drawn back and then recombine and emits a photon of a much shorter wavelength than the laser that caused the tunnel ionization. And this was then something called high order harmonic generation. And what you see here is the intensity of a photon coming out from the interaction of a short high-intensity laser pulse and an atom, say neon or some other rare gas. And what was observed then was that first there is a drop in intensity. Then there is a plateau where the intensity really doesn't change very much. And finally, there is a cutoff in the intensity. So in a way, you can say that this is a way to generate extreme ultraviolet light that you can use in experiments. But it was also a way of realizing that to understand this behavior, the decrease, the plateau, and the cutoff took a lot of theoretical development in the early 1990s. And once the basic physics behind this had been understood, there was a further development to exploit this mechanism, which is a 3-step recollision mechanism. And it was realized that it's possible actually to explore this mechanism to create even shorter pulses, to break through the 1 femtosecond pulse duration limit. And the first breakthrough paper in that respect came in 2001, and with the name attosecond metrology. So one can say that the access to CPA-based laser system led to development in atomic molecular physics, first into the strong field physics and then into attosecond metrology. And now there are many groups working on studying attosecond physics, where you can really study the, shall we say, the motion of electrons. So you remember I told you that in the 1990s, Sibel and many others, of course, also studied the motion of atoms in molecules. Now one can study the motion of electrons in atoms, where the time scale is even much shorter, but you can come down to maybe 100 attoseconds or so. If we look at the high intensity limit, I mean, where you want to have low rep rate but very high laser intensity, these lasers are called Petawatt lasers, and here is a way to illustrate how these Petawatt lasers have developed in the world. So it really started in the US. And Moreau and Strickland did their invention when they were at the University of Rochester in upstate New York. And there are still, of course, many developments in the US, but you can see this is the integrated petawatt capacity in the United States, Europe, and Asia. And Europe is presently leading in this area, and with Asia number 2 and United States number 3. So there has been a bit of a concern in the US that a field that was really initiated in the US, where they have now fallen behind a little bit. And I mentioned this extreme light infrastructure, which is now under development. And there are 3 different laser systems that are being developed. One in Czech Republic, one in Hungary, and one in Romania. And they have a little bit different approach. The one in Hungary will focus mainly on generating attosecond pulses for users, whereas the one in Czech will approach the high intensity frontier, and the one in Romania will be more targeting nuclear physics. All of these systems are now in shall we say, commissioning or developing phase, not yet, as far as I know, open for users, but it will be a little bit of an approach more like synchrotron radiation sources. So instead of having your home lab with your own laser, you apply for beam time, you come with do your experiment in a facility where somebody else is handling the beam for you. So now I mentioned the development into basic science, the strong field physics, the attosecond. Now let's look at a little bit of application also, because I think what was one interesting aspect with the CPA technique was that it sort of gave 2 different directions, one into basic science and one into more practical applications. And the first example is, and this is now when you have typically 1 hertz and maximum intensity, petawatt intensity, and you want to do laser-driven acceleration. So typically, and here we see the most advanced laboratory in this respect is called Bella at Lawrence Berkeley National Laboratory. And so you have a drive laser, this very strong laser, an electron injector, and then you have a plasma here. And the drive laser will create a plasma wave on which the electrons are surfing and where they can acquire a very high energy over a very short distance. So this distance can be maybe just 10, 20 centimeters or so, and you can accelerate the electrons over this distance to maybe 10 GeV. And this is a gradient much higher than you can reach with, shall we say, the mature radio frequency technology, which is the one which is used in almost all accelerators these days. So here I think we can see now a development where RF technology slowly will be replaced by this laser-driven technology. And there are, of course, 2 different aspects of this. One is that if you want to go to very high, shall we say, pushing the energy frontier in high energy physics, it's going to be very difficult and very expensive if you want to go to higher energies. Let's say now at LHC they operate at 2 beams, colliding beams at 7 TeV. Let's say you want to go to 100 TeV, for example. You can certainly do it with RF technology, but it will become extremely expensive and a very huge machine. So pushing the energy frontier, one way to do it would be with laser plasma technology. Of course, it takes a long time from a demonstration to have a mature technology that's sufficiently robust so that you can implement it in an accelerator. But I think this is an interesting development. Another development, I think, which will also be of more practical use is for cancer therapy. I mean, the dominant radiation source for cancer therapy treatment is X-rays. But X-rays have certain disadvantages because you cannot deposit very accurately the amount of radiation you want on the cancer tumor. But you can do it with protons because of it's something called the Bragg peak. I won't go into the details there, but a proton accelerator is a much more elaborate equipment for a hospital to operate than an X-ray source. So typically there are literally thousands of X-ray sources for cancer treatment, but not very many with protons. And if one could use this laser plasma technology to build an compact accelerator, small compact accelerator that would easily fit into a hospital environment, I think that would be a really important step. But this is still in the future. We'll see. What's not in the future, but is definitely used this day in industrial applications, is to use these high rep rate femtosecond CPA-based lasers to for example, drilling or making, for example, stents where you need a very narrow channel, but very narrow and very long channel. So here is a comparison then between a nanosecond laser interacting with a material and a femtosecond laser. And the nanosecond laser, and here you see the time scale, by the way. I mean, going from 1 second, here we have nanosecond, which is typical time scale for fast electronics. Femtosecond, then we are down to photosynthesis. And here you have attosecond, the electron motion around an atom. And with nanosecond laser, you get a heated area. There is much more heat transfer and shock waves that cause damages. Whereas the femtosecond laser, the pulse is so short, so that it's basically a cold technique. I mean, you can really deposit the effect very accurately, precisely where you want it, without causing any damage in the surrounding. So you can see that's the reason why you can make such a very fine, narrow channel here, without causing this type of damage that you see with the nanosecond laser. And I think that if you come down to about 5 femtoseconds, the thermal damage is almost negligible. And here we can then make an interesting comparison. You remember that I told you that in the mid-1980s, 5 femtosecond, that was a really advanced research laser that was operated in university groups, but took, of course, several PhD students and postdocs to operate. Now you have femtosecond lasers that are commercial. You can very robust. They can be used in industrial environments. It's just turnkey. I mean, it's a completely different situation. And this has also led to something which I find interesting because I'm very nearsighted, has been for since I was a teenager. But it's now possible to make corrections of myopia or nearsightedness. And there are, and this technique, which is now, there are different techniques, but the one which is shown here is an all femtosecond laser-based technique. So that what you want to do is to change the refractive power of your optical system in the eye. Basically, for a nearsighted person, the eye is too long. So that you want to reduce the refractive power. So what the femtosecond laser is doing is to create a small lenticule, which is a piece of tissue in the early part of the eye. And this can then be extracted. And so it's called, so you use the femtosecond to create it first. And then you make a small hole, small incision. And then you can extract the lenticule. That's small incision lenticule extraction. And this is an operation that's done in maybe 20 minutes or so. And it's quite remarkable. I mean, if I had this possibility when I was a teenager, of course I would have done it immediately. And you can see here then a commercial system which is used in these eye surgeries, which is a femtosecond laser system where the surgeon just have to push buttons, and I'm sure everything is computer controlled and so on. And there was an article in The Lancet, which is one of the leading medical journals in some years ago, and where they point out that myopia has emerged as a major health issue in East Asia, in China, Japan, Korea, and where the number of school children having myopia is up on the level of 80 to 90%. It's an extremely high percentage. And one possible explanation could be that they spend maybe too little time outside, where their eyes have to adjust to different distances, and maybe too much time spending on a screen or a book. And this leads to nearsightedness. So I'm coming to the end, and if you want to read more scientific background, popular descriptions, and so on, you can always go to nobelprize.org. So there you can find references and a lot of material. So with this, I thank you for the attention.
Thank you so much for a wonderful overview, and also for the exciting perspectives, both in basic research, but also useful stuff. I have to say, I'm glad you said that both books and screens may cause myopia, because I have a kid and he's spending too much time in front of his screen, but then maybe books would be just as bad.
In my case, it was genetic.
Okay. Yeah, I can always look for that. All right, so we have time for a few questions, and then somebody will pass the microphone around. Come
on. You mentioned that there wasn't really a roadmap to higher intensities after the mid-80s. What's the roadmap like today? So your graph pointed at just increasing.
I think that I don't see any real showstopper. I mean, I think now it's going to be more of an engineering problem rather than a basic science problem. I mean, you have to find materials suitable and so on, and scalability. I mean, it's clear that this technology is scalable in a way that was not possible earlier. So
there is still room for just going with this technology, I think so, yes, until we reach the next.
I think we will see an increase and an increase, but
I have two questions. First, if I remember correctly, optical trapping is done mainly by CV laser, right? And
CW laser?
Yeah. And what's the reason why they use CV, not pulse laser? And second question is, on the first part, I mean, my assumption is that they use Gaussian beam, right?
Yeah.
What happens if you use different, let's say, flat top, or especially, let's say, Bessel beams, non-diffractive Bessel beams?
The first question I'm not sure I understood, but if we take the second question, I mean, clearly you want to use, I mean, a Gaussian beam is always the most convenient for.
Yeah, for sure.
And if you align mirrors and so on, you know that you always try to get the Gaussian beam, and you get the effect you're looking for. So I don't think there is any any particular push for another type of beam profile. The first question, I'm not sure I understood completely. You mentioned CW laser and
Why
heating,
people use more CV rather than pulse laser? What's advantages of CV laser in comparison with pulse laser for optical trapping?
Well, I mean, it's a matter of the application. I mean, if you want to do high-resolution spectroscopy, and obviously the choice is CW laser operating at a very narrow frequency.
Yeah, yeah.
I mean,
But
but if you want to do time results experiments, and in particular look at very short time scales, then the obvious choice is these ultra-fast lasers. So I mean, if you look at the history of the Nobel Prize in physics since 1964, you can see that there has been several prizes where the CW laser has been the important contributor. I mean, you have laser spectroscopy early 1980s. You have laser cooling, for example. Obviously, that's where you need a CW laser. You have the creation of Bose-Einstein condensate in an ultra-cold gases. Once again, you need a CW laser. So maybe this was the first time where really the pulse laser is given. Well, the Seville Prize in chemistry, obviously, was.
Yeah.
So
Yeah, thank you.
Yeah.
Anyone else? Okay. Thank you so much, Mats Larsson.
Thank you.